Okay, welcome back to the class. Um, so I hope you can see my screen, right? Okay. So let's begin by recalling what we discussed last time, right? Which are general applications of linear algebra. What are the most interesting and popular problems where linear algebra and the foundations of data science concepts are used, and what sort of tools we require to solve some of these problems in an efficient manner. So we did talk about dimensionality reduction technique by using some of the foundational concepts of linear algebra. We talked about PCA, right? We gave an example from a workload characterization technique, and we figured out that if there are two factors contributing to the workload, then using principal component analysis via the tools of linear algebra, we can figure out of these two factors which one is the most influential, okay, and thereby reject the other one, right? And try to figure out ways to, in that particular problem, try to figure out ways such that the principal factor which is contributing to the workload, could be more efficiently managed, right? Okay. I also said that, I would mention a few of the technical terms without getting into the details of it, right? Now, this is the second class, and the first class was basically give you an idea of why you should study linear algebra, right? And so this is the second class where we start talking about some of these principal ideas, okay? As I said, the first couple of weeks, the classes are, we'll wander through different ideas and concepts in linear algebra, and the more rigorous treatment of each one of these concepts will begin from the third week, okay? However, you should not miss one single thing which would be constant throughout this course, is that the treatment of matrices, the treatment of this course via matrices and matrix computation more precisely will be avoided at all costs, okay? There will be very few instances where we will actually compute the determinant of a matrix. There will be probably one instance where we will compute the inverse of a matrix, because those are not the things that we are interested in. Okay, what we are interested in is that if there exists a matrix or a linear transformation, does it inverse exist, right? And if the inverse exists, what do we do with it? Okay, and if the determinant exists, what do we do with the determinant, right? What kind of problems we solve? Because if you know the inverse exists, sometimes that's a very difficult question to answer. If you know that the inverse exists, then there are hundreds and different types of tools that you can use which will give you the matrix, inverse, and the determinants within a jiffy, right? So you really don't need to crunch matrices here. So this course is not about crunching numbers, okay? All right. Okay. So some of the tools and concepts that are really, really important in linear algebra are, and I have mentioned some of these concepts. If you recall, I mentioned inner product, I mentioned eigenvalues or characteristic values, as you can see in this slide. I talked about projections, I talked about orthogonality, right? I just mentioned this, I should not say I talked about this, I mentioned linear independence, and I mentioned linear independence, orthogonality, and eigenvalues in the context of PCA, right? And there we said that there are a bunch of very, very important results in linear algebra which are used, right? One is that if your matrix or the linear transformation is a symmetric one and real and symmetric one, then the corresponding eigenvalues are real and distinct. And that's a very important result. And if those corresponding eigenvalues are real and distinct, the corresponding eigenvectors are orthogonal to each other, which are exactly the principal factors of PCA. And if there exists a set of vectors which are orthogonal to each other, we can also show that they are linearly independent. Okay, and this linear independence is a very, very powerful concept because the linear independence and the span of vectors together give us the idea of basis and dimension of a vector space. So if I tell you what is the size of a matrix, you could actually go to the corresponding linear transformation defined in a particular vector space. And by looking at the basis of that vector space, you can easily figure out what is the dimension of the vector space. This is particularly useful in high dimensional classification problems. In particular, I'm not sure if you are familiar with support vector machines and VC dimension. I don't know whether you know what a VC dimension is, but what a VC dimension talks about in classification is that if a problem is not linearly separable, right, in lower dimensions, you use something called a kernel, right? You use a kernel trick to project it to a higher dimension. And what happens is so when you project to a higher dimension, the number of features, the dimensionality of the problem also increases, right? But in a higher dimensional vector space, that non-linearly separable problem becomes a linearly separable problem. And that's a very beautiful idea that Vapnik used to solve non-linearly separable problems in lower dimensions. Okay, so figuring out these things is really, really important. And there is a very important result which says that if the dimensionality of your space is m, then the number of points you can actually classify, okay, or you can shatter using a linear classifier is m+1. That's a very, very important result. Okay. Next semester, if you take my course on computational learning theory, which is an advanced version of the basic machine learning course that some of you are probably taking, we will be talking about these things. Okay. All right. And if you don't take the linear algebra class, and if you don't take this particular class and understand the concepts well, you will find it really, really hard to, grasp the concepts there. And then there are some geometrical interpretations of linear algebra that we should talk about. Least square optimization is one of those, right? Okay. We already gave some geometrical interpretation when we talked about principal component analysis, right? Okay. And then there is another very important concept called rank. So what is a rank of a matrix, or correspondingly, what is a rank of a linear transformation? Please also know, and I will of course repeat this over in the next couple of lectures, is that whenever I talk about a matrix, I mean a matrix induced by a linear transformation. Okay, so I would use these two terms interchangeably, and as the course progresses, my use of the term matrix will reduce. I will be not using the term matrix frequently, rather I'll be using the term linear transformation more frequently. Okay, because we would want to look at abstraction of the structure and the different properties of a linear transformation. So whatever you know about matrix, know one thing. Whatever you know about matrices and their properties, all of those things and properties are interpretable and quantifiable using linear transformation. But it gives you a much more representational power because you really don't care how big the matrix is. Okay, all right. So these are some of the very, very important concepts, and we will hover through these concepts slowly. Okay. So, but I still, because this is still a class where mostly we'll talk about linear algebra, there are standard things that I would want to just mention, because I don't want to suffer from the guilt of not telling you what a vector is, how do you do vector addition and things like that. But that's not the focus of this course. Okay. All right. So you can think of vectors as a directed line segment. Okay. And in multiple dimensions. So in 2 dimensions, you can represent a vector in a coordinate geometry system. And that's the beauty of it, right? I mean, you can think of a vector. I mean, if you look at the, picture, you can think of a vector as sort of a coordinate in 2 dimensions. You can think of a vector as an x comma y, and that's it, right? And if you draw a directed line segment from the origin to a point in the first quadrant, for example, and denote the coordinates of that particular point, wherever your directed line segment stops, call it x comma y, then in vector algebra, or the kind of vector algebra that you are exposed to, I mean, you can measure the length, right? And you can also call that vector x, right? In this case, whenever I say a vector, what I mean is that it is actually some position in a coordinate system. So in a 2-dimensional coordinate system is x comma y. In an n-dimensional coordinate system, it will be x1, x2, x3, all the way up to xn, right? In a column vector, right? And therefore, it imparts the dimension of the vector space. right? What you need to do to understand this basic geometry in higher dimensional vector space is that you need to define a nice basis. Okay, what is a basis? Don't worry about it now. We'll come to it very soon. Okay, so you know how to add two vectors, right? I mean, you move a vector to one direction, move it to another direction, right? And use the parallelogram law to find out the resultant vector, right? Which is a simple algebraic addition. And this is a scalar product. Okay, now, I mean, I give you a vector, okay? And then I multiply this vector by some real number, let's say, for now. Okay, so you have a vector x comma y, and you multiply it by some number 5. So what do you expect? What do you expect? I mean, if you multiply by a number greater than 1, you would expect the length of the original vector to increase, right? So you are sort of dilating it. If you multiply a vector by some number which is between 0 and 1, what do you expect? You would expect that the resultant vector will be contracted. Okay, so by simply using a scalar, you can dilate and contract a vector without changing its direction. Okay, all right. Okay, now remember, whenever we do a matrix operation, which is when we multiply a matrix with a vector, we can actually change the length, direction, and also the dimensionality. Okay. Now, dot product, you know what a dot product is, right? I mean, and what do you do with a dot product? I mean, I've given you two examples, right? One from support vector machines and one from a matrimonial / dating site, right? I mean, from a dot product, there is because a dot product is nothing but, I mean, if you take the dot product of two vectors, it's a transpose of one multiplied with another vector, but you can write it as an inner product form. If you take the dot product of a vector with itself, you actually end up getting the length of the vector, square of the length of the vector, right? Okay. And also dot product, as you know from vector algebra, is nothing but the dot product of two vectors is the product of the length of the two vectors multiplied by the cosine of the angle between them, which is why if two vectors are orthogonal to each other, right, that you know their dot product is 0 because theta is 90 degree and cosine of 90 degrees is 0. Okay. All right. So in matrix algebra, vector algebra notation, a dot product is nothing but a number. Okay, so if you take the dot product of two vectors, it gives you a number. Okay, so basically, what do you do with a number? Okay, other than the fact that you figure out whether two vectors are orthogonal to each other, this is very, very important in the context of projections. If you recall, in support vector machine, I showed an example, right? I told you that if there are objects belonging to two different classes separated by 2 or 3 lines, right? And if one object is mistakenly falls into the region of the other object, what we can do is that we can project it in a direction perpendicular and project it to the other side so that the chances of misclassification are reduced. Now, how are you going to project it? You can project it by, you know, as I just told you a few minutes back, you can project a vector by simply not changing its direction, but by changing its length, right? So you can exactly do that by multiplying that vector with a number or a scalar. Now this scalar is given to you by its inner product. So this is directly influential in projecting a vector from one space, I mean from one region to the another region. That's why it's particularly useful. Okay, all right. So you can express a dot product in a coordinate form, or you can also express a dot product by or inner product by the, you know, using transposes and things like that. Please understand, whenever you are probably familiar with a transpose of a matrix, but whenever I'm talking about any operation that I'm talking about here, I actually imply all of these operations in the context of a linear transformation. Now you may ask at this point of time, sir, what is a linear transformation? Have some patience, we'll get to that. Okay, then there is this basis and orthonormal basis, right? And this is something that I would like to talk about. So what happens is, let me go to my whiteboard. So can you see my whiteboard? Right?
Yes, sir.
Yes, sir.
Can you see my whiteboard? Okay, good. Okay, all right. So yesterday, I mean, the day before, the day I received this, graphic tablet. I practiced a little. I mean, I assure you, my handwriting is not as bad as it appears here. Okay, I write much more legibly and much better. But I mean, I guess this will take some time for me to practice, right? So we are talking about a basis, right? So I mean, imagine you are in a two-dimensional space. Okay, all right. Okay, all right. Now, if you look at this two-dimensional coordinate system, I mean, you will have a bunch of different values along the x-axis and bunch of different values along the y-axis, and you know, depending on the also on the quadrants, which quadrant your point lies in, I mean, you will have different signs of x and y values, right? Okay. So, but let's just for now focus on values along the horizontal axis and values along the vertical axis. Okay. So if I go here, probably here, right? And I'll just call this 1, 0. Okay, all right. And then I come back to origin, move a little up. See, don't make fun of my drawing, okay? However, you can make fun of it, but you know, I'm usually, when I work on the board, I'm usually not as horrible as it appears here, I assure you. Okay, all right. So now, so you just imagine this. Now, this is just one vector along the direction of the horizontal axis, right? I mean, parallel to the direction of the horizontal axis. I mean, can we not cook up a bunch of other vectors along the direction of the horizontal axis on the positive side? We can, right? So, for example, we can actually travel a little farther on the horizontal axis, right? And we can actually cook up another vector. Okay, now we have two vectors on the horizontal axis, 1, 0 and 4, 0. What is the relation between the two? That this guy, you know, this guy is nothing but four times this guy, right? Okay, so what's the point? The point is, I mean, if you figure out a sort of one standard vector along the direction of the x-axis, and in this case, let's assume that the standard vector is 1, 0. Using 1, 0, you can actually cook up any vector along the horizontal axis, isn't it? Right? I mean, you multiply 1, 0 with 10, you get 10, 0. You multiply 1, 0 with -3, you get -3, 0, which is a vector on the negative side of the horizontal axis, right? And I can simply port the same operation on the vertical axis as well, correct? I mean, I can cook up, if I assume that this 0, 1, this particular 0, 1 is just a standard vector along the direction of the vertical axis, I can use any scalar multiple, right? Any scalar multiple and cook up other vectors along the y-axis, right? Okay. So now together, now let's write something here. So what I have here is one vector 1, 0 and another one 0, 1. Okay. Now both of these vectors belong to. Would you agree? Are you familiar with this notation? Are you familiar with this notation? I guess, yeah, right? This is R2.
Yes, sir.
You have a two-dimensional plane on real numbers. We're just discussing about real numbers, right? Now this R2 is, let me call this as a vector space. This R2 is a vector space. Why am I calling it a vector space? So what exactly is a vector space? Informally, a vector space is nothing. You can think of a vector space as a set. Okay, it's a set of ordered pairs. Okay, all right, it's a set of ordered pairs. Now in this particular case, it's not only ordered pairs, it's actually a set of ordered n tuples, right? Okay, so what will happen is I mean, you cook up a space, a geometric space in lower dimensions or as well as higher dimensions, doesn't matter. And this space does what? This space contains all the types of vectors that you can possibly imagine. So when we talk about R2 here, I mean, what I imply is that this is a vector space which will contain all two-dimensional, like 2x1 column vectors, right? Okay, all right. So a vector space is one which contains your column vectors. It stores all of your column vectors, right? Okay, all right. Now, what are you going to do with this kind of column vectors? Actually, the whole idea is if you have two vector spaces. So I'll just give you a motivation of this. Why we do this? The why this is important is that, let's say I have some operator, I mean some function, forget operator, you are familiar with functions, right? So let's use this. So I have some function t, which what I want to do is that I want to map this function from R2 to itself. We can do that, right? I mean, from your calculus ideas, you know that there is a function. I mean, you can cook up a function which can take input from a space, right, and map it to an output space. So there is an input space and there is an output space. So in this case, your input and output spaces, both your input and output spaces are R² vector spaces. So what resides here? A 2x1 column vector resides here. What resides here? A 2x1 column vector resides here. So when you use a linear function on these column vectors, then your outcome or your product becomes a 2x2 matrix. Okay. This is how we actually generate matrices. Matrices do not come from, thin sky. Okay. So what I intend to mean is, because you remember I said that I will be using matrices less frequently and linear transformations or linear maps more. So by this relation, what I imply is that there exists a linear map between vector spaces, okay, such that the matrix is, the matrix is induced by the map. Okay, so whenever I talk about a matrix, remember this, I'm talking about a matrix. What I imply is a matrix induced by a linear map or a linear transformation. Okay, that's where matrices come from. So when you see a matrix, a 2x2 matrix, a 3x3 matrix, you are usually accustomed to thinking, oh, there are elements in each one of these places. If it's a 3x3 matrix, there are 9 elements, right? Okay, and you can index each one of these elements, right? You have probably written codes in C, C++, with matrices, multiplication, addition, computing the inverse of a matrix, right? But you have always thought of the elements of a matrix as a pointwise. But this is not a pointwise thing. This is actually when you look at a 2x2 matrix, right? So what I typically imply is the following, that if I have an identity linear map, let's think about this, okay? If I have an identity linear map that I actually work on these two vectors, 1, 0, 0, 1, okay, and wrap this around, what I should actually get, if my linear map is an identity linear map, what I should actually get is this. Okay, so this is how matrices are generated. However, I have another point to make, because we were talking about what? We started talking about a basis, right? I mean, we wanted to see what a basis is. So what you can say is that these two guys, these 1, 0 and 0, 1, form a basis of this vector space R2. Okay, so this is once again another claim that I wish to make here, is that this 1, 0 and 0, 1, okay, these two vectors form a basis of R2. Remember, just one thing, sometimes even a small one particular letter becomes very, very important in what you are trying to convey. I wrote form A basis. I did not write form B basis, which means this particular vector space R2 is entitled to have other bases as well. Okay, but this is the most standard and the minimal. Now, let me sort of go back and let's see what else we can do. So let's say I have, cooked up another vector that also belongs to the same vector space, isn't it? 1, 1 that belongs to R2, right? Now, how can I write 1, 1 as a linear combination of the two existing vectors? This is what I can do, right? So I can write 1, 1 as alpha times 1, 0 plus beta times 0, 1, where these alphas and betas are just scalars. I mean, in this case, it's really easy to figure out what these alphas and betas are, right? But I mean, alpha is 1 and beta is also 1, right? But generally, what I want to say is that this 1, 1, which is another vector in belonging to the same vector space, can be expressed as a linear combination of these two existing vectors, 1, 0 and 0, 1. Okay. Now, can you think of any vector in the same vector space which cannot be expressed by 1, 0 and 0, 1? No, right? In fact, everything under the sun, as far as this R square is concerned, and R2 is concerned, can be expressed as a linear combination of 1, 0 and 0, 1, right? Like for example, I mean, if I take 7, 4, I can write it as alpha 1 times 1, 0 and beta 1 times 0, 1, where alpha 1 is 7 and beta 1 is 4. So what am I trying to say? What I'm trying to say is that if this 1, 0 and 0, 1 form a basis of R2, then any vector representation in the same vector space R2 could be accomplished by using a linear combination of these two. And that's the reason these two guys, 1, 0 and 0, 1, together is called a basis of that particular vector space. Not only that, I mean, this is too simple. This is too simple, because in order to call something formally as a basis, two properties need to be satisfied. Okay, so let me erase this canvas for now.
Sir, can you please explain what is a linear map and what do you exactly mean by the definition linear map between vector spaces?
So let me erase this.
Induced by the map.
All right, let me come back to this. Okay, so I'll just.
Sir, am I audible? Hello.
Clear the canvas. Okay, all right, and go back to the black pen, and it's time for a few definitions. Okay, all right. So one is a basis. Okay, Because if you recall in the PowerPoint, there are few terms that you have seen, right? You have also seen span, right? And you have also seen linear independence. Okay, all right. So let's let's talk about a basis. So I would say, I mean, I'm just giving you a very simple two-dimensional example first. I would say that x comma y is a basis of a vector space if and only if, number one, x comma y spans the vector space. That's number one. And number two is that x comma y, this set is linearly independent. Okay, all right. Now, let's look at the first point. Okay, so I said that this will span the space, right? What do I mean by that? Now just think of it visually. Try to imagine this. Let's say, I mean, you are in a real classroom. I don't know when you are going to get back to a real classroom and when am I going to get back to a real classroom. But let's say we are in a real classroom now, which is three-dimensional, right? Okay, three-dimensional. That means what? I mean, if you want, you walk along the length of the classroom. If you want, you can walk along the width of the classroom. And if you're a Spider-Man, you can walk along the height of the classroom as well, right? Now, while you are performing any one of these three tasks, which is you're trying to span yourself along the horizontal axis, you can use a vector 1 comma 0, 1 comma 0 comma 0, because it's three-dimensional, right? Okay, all right, okay, so let's write that over here. So we are now taking a three-dimensional example, 1 comma 0 comma 0. Okay, this is along the what? X-axis. And then along the y-axis, you can use this vector to walk, right? And then along the z-axis or z-axis, you can use this vector. Now, if I use all three vectors together, can I not actually walk to any point in the three-dimensional room? I can, right? So any point in the three-dimensional room, x, y, z, right? I'm just expressing using this transpose now because it's really a column vector, can be written as x times 1, I'm sorry, x times 1, 0, 0 plus y times 0, 1, 0 plus z times 0, 0, 1. Okay, all right. So can I say this 1, 0, 0, 0, 1, 0, and 0, 0, 1 spans the three-dimensional vector space R3. Can I say that? Yes, I can, right? I can say this. So that's the first condition. So this is what I mean by span. But is this the only set of vectors that span the space? No, there could be other set of vectors as well, right? But any other spanning set can be written as a linear combination of this spanning set. Okay, so this is called the fundamental spanning list of any vector space. Now, if I scale this up, guys, if I scale this up, then, and you know that these are unit vectors, right? I mean, E1, E2, and E3. Now, if I cook up something like this: E1, E2, all the way up to En, where n could be any dimension, finite of course, but could be any dimension, right? What would that imply? Wouldn't it imply that this set of vectors will span an n-dimensional vector space Rn? Okay, all right, and that's about it. Now the next question is, so if this is settled, let me go back to the Google Classroom and see if there are any questions that you guys have at this point of time. Oh, there are a bunch of questions. Guys, just hold on, okay? I will see you. Yes. See, some of the questions that you were asking, like linear transformation and all of that, right? Do not think for a moment that I am in the class to throw keywords at you. If I'm saying something, I will explain, but I have a certain style of doing things. Okay, so all right, so let's go back to the whiteboard. Okay, I will talk about what a linear transformation is. Definitely, I have to, because that's the core of the class. Okay, but my intention was to first talk about the more fundamental founding blocks of a vector space, right? Because you define linear transformations on a vector space. The second question, because we are trying to figure out what is a basis. Now, what we said at this point of time, that this guy spans the vector space. But is it a basis? Is this guy a basis as well? How do we know this? So in order to establish that this is a basis, what I need is that I need to show that, what I need to show is this guy, this set of vectors are linearly independent as well. Now, what is linear independence? In very, very simple terms, if I forget the formal statement, in very, very simple terms, two vectors are linearly independent if you cannot construct one vector from the other vector using scalars. The only thing that you are allowed to use is a scalar, right? So, for example, if I give like 1, 0 and 3, 0, these two are not linearly independent, clearly, because the second vector is just 3 times the first vector. Okay? However, 1, 0 and 0, -1, these two are linearly independent, because there is no way in hell you can construct the second vector from the first vector by using a simple scalar multiplier. You can't. Okay, all right. So in general, if you look at these standard vectors like 1, 0, 0, 0, 1, 0, and 0, 0, 1, these are also linearly independent of each other. Okay, for the simple reason, because the position of 1, the position of the non-zero element is changing. If the position of the non-zero element did not change, I could express y easily in terms of x and vice versa. Okay, all right. So this definitely spans R3 and definitely is a set of linearly independent vectors, right? Okay, and therefore these guys form the basis of R3, and similarly these guys, they form the basis of Rn, because they span the set, they span the vector space, and they are also linearly independent of each other. Okay, all right. Now a more formal, introduction, a more formal talk about what exactly linear independence is. Okay. So what exactly is linear independence, formally speaking? Okay, I'll start with a set of two vectors. So if I have a1 x1 plus a2 x2 equal to the 0 vector. Okay, all right. This, and if this implies that this equation is true and the scalars a1 and a2 are identically 0, then I can say that x1 and x2 is a linearly independent set. This is very, very important. It looks simple, but it's really not that simple to digest. Okay, I have seen people misinterpret that all the time. So how does this make sense? So let's assume that this is not true. Okay, so let's assume that a1 x1 plus a2, oh damn this, a2 x2 is equal to 0, but a1 is not equal to 0 and a2 is not equal to 0. Okay, does it still make the set of vectors x1 x2 linearly independent? Now what we can do is I can simply rewrite this equation in the following manner, right? And then I can write this. Would you agree that this is fine? Okay, so if you look at this, what is this? You are able to express one vector, just like 3, 0 and 1, 0. You are able to express x1 in terms of x2, right? If a1 is not equal to 0 and a2 is not equal to 0. What would that imply? That would imply that x1 and x2 are not linearly independent, because you can cook up one vector from the other vector, right? Okay, so how does this condition a1 and a2 both identically 0 make sense? Let's go back to that boxed guy. Okay, let's go back here. Now think about this. If both a1 and a2 are identically 0, then there is no way that the equation itself, the relation or the equation or the relation between x1 and x2 doesn't hold, right? And therefore, these two are equivalent. So therefore, whenever you have a linear combination of vectors set equal to 0, and if and only if the scalar coefficients a1 and a2 in this case are identically 0, then only the corresponding set of vectors x1 and x2 would be linearly independent. Think of 1, 0 and 0, 1. They follow this exactly. Okay, all right. So therefore, now we can formalize this definition of linear independence, because this forms the crux of what we are going to do. So formally, what happens is, if there is a set of vectors equal to 0, okay, then a1, ai equal to 0 for all I from 1 to n, then only what implies is the set of vectors xi is linearly independent, otherwise not. So this is the formal definition. Okay, so now if a set of vectors spans a vector space and as well as they are linearly independent of each other, then only that particular set forms a basis. Why do I need a basis? You may ask a question like, so what is a so this definition is really important to define a basis, right? Okay, and what do I get by knowing the basis of a vector space? You know, I'll just write this one straight away, that if you know the basis of a vector space, you know the dimension of the vector space as well. Okay, example, guys, R2. Okay, what is the dimension of R2? R2 is a two-dimensional vector space, right? So what is the dimension of R2?
Two.
What is the dimension of R2? 2, right? Why? Because you have 1, 0 and 0, 1 as the basis of R2, right? So therefore, what is the length of this basis? What is the length of this basis? The length of this basis is simply the number of column vectors or the number of vectors that particular set contains. How many vectors does this set contains? 1, 0 and 0, 1, right? 2. Okay, and that is why the dimension of R2 is 2. Similarly, the dimension of R3 is 3 and dimension of Rn is n. Okay, so that's why I mean, using basis and linear independence, we can very easily figure out what exactly is, you know, the dimension of a vector space and how many basis vectors you actually need to construct. Okay. All right. Now, let's go back to the slides. Okay. All right. So here we are talking about basis. Don't worry about orthonormal basis for now. Okay. We'll come to that, you know. And then this, what is a matrix? Matrix is nothing but, you know, a concatenation of column vectors, as I have already shown it to you. Okay, all right. And then there are basic matrix operations. I mean, I'm just saying this because I have an obligation of saying this. And we are not going to do matrix additions or matrix subtractions or, you know, matrix multiplications in this class. Okay, so those things are juvenile. Okay, but I mean, you should know that these are the standard operations that, I mean, one should do. One important question is the matrix multiplication commutative? Generally, no. Okay, so if you change the order of the matrices, you are not going to get the same answer. Okay, all right. That is once again because the corresponding linear transformation is not commutative. Okay, all right. And you can multiply a matrix with a vector to generate another vector, right? Which is exactly what a linear map does. Okay, all right. And here I just want to illustrate this. Okay, all right. If I have the time, I think I have some time. So let's go back to the whiteboard. Here is this. So what I want to do here is the following. Okay, drop a vector x comma y and reflect the vector in the opposite direction. Now, if I do that, what I'm going to end up in getting is x minus. So what we have done here is nothing but reflection, right? Now the question is this a linear map? I'm sorry. Is this a linear map? Okay, all right. So I mean, what do we want to do? I mean, because this is our input, right? This is our input, and this is our output. Okay, all right. So what I want to generate is that there is this vector which is x minus y here, and then there is another vector which is x and y, right? Of course, I mean, you cannot just transform an x y column vector to an x minus y column vector by black magic. You need some linear map, right? So let's say I have used the same notation before. So here capital T, which is a linear map. So I want to do this. Okay, all right. Okay, so what happens is, so let's call this x meaning a vector, right? And what I end up getting in is T of x. Okay, all right. Now how do we do that? Obviously, you would say that I should be able to multiply this column vector on the left with a matrix, right? And I should be able to get this. Pretty simple, right? Yes, I agree with you. So what would that be? So let me just define the matrix induced by the linear transformation, and by simple visual inspection, right? I mean, if you cook up this particular matrix, okay, and you take this matrix, multiply with the column vector x comma y, you are going to get x comma minus y. Okay, so your job of reflection is being done by multiplying the matrix with a vector, input vector, right? Okay, and what this linear transformation or the matrix has done is that it has taken you from R square to R square, right? Because you are not being projected to another vector space. Your vector spaces are of the same dimension. And more importantly, in the process of doing this, you actually ended up using the basis vectors of R2, which are 1, 0 and 0, minus 1. Okay, all right. Am I out of time? I have still 5 minutes. Okay, so let me show you. So because you asked what a linear transformation is, right? So let me show you another linear transformation, okay, which is also interesting, right? So many of these operations, that geometric operations that we do, is actually nothing but a linear map. So what does a linear map do? It takes your column vector from the input vector space, and maps it to an output vector space. Nothing exactly the same thing that what a function does, but it's strictly a linear function and therefore follows certain properties. Okay. However, let me once again, show you something else. Okay. So let's say I have this guy x, y, which is at some angle alpha with the horizontal axis. I have okay, all right. So this is x. This is. So the final output is actually this, right? So you first rotate it to an angle alpha, Okay, so that you have and this is just a radius vector, right? Radial direction. So the magnitude of the vector is not changed, okay, but you have changed the orientation, right? So therefore, what I see straight away is that x equal to r cosine of alpha and y equal to r sine of alpha. Okay, what I also see is that w equal to r cosine of theta plus alpha, isn't it? Right? And v equal to r sine of theta plus alpha. Okay, guys? Yeah? Okay. Now, if I expand this out, so it's w is r cosine of theta cosine of alpha minus r sine of theta sine of alpha, right? And v is r sine of theta cosine of alpha plus r cosine of theta sine of alpha. This is some trigonometric identities. Interestingly enough, you see there is this r cosine of alpha, right? And r sine of alpha. What are these? You know that r cosine of alpha is x, right? And so therefore this is x cosine of theta. And you know that r, sorry, there is a minus, sorry. And you know that there is r sine of alpha, so that is y. So there is y sine of theta. Here also you can do the same thing. R cosine of alpha is nothing but x. So this is x sine of theta plus r sine of alpha, which is y cosine of theta. Okay, so now if I combine these two equations to a matrix form, I have wv, okay, right? And then also what I have is xy. Isn't that what we wanted to do? What we wanted to do is the following, right? Like I would want to figure out a transformation T, which will take me from xy to wv. And basically this is rotation, what we are talking about, because this is exactly what we have done, right? It's a rotation. Now, how do we achieve this rotation? Simple. Cosine of theta minus sine of theta, right? You simply read off from the equations, right? And sine of theta and cosine of theta. What is the determinant of this rotation matrix? 1. Okay, all right. And so this is nothing but a linear transformation. This is nothing but a linear transformation induced. It's a matrix induced by the linear transformation, and this is known as rotation transformation or a rotation matrix. Remember, even if you are rotating, right, geometrically it's a nonlinear operation, right? But you are able to accomplish that by using a linear map. Okay, so this is where I'm going to stop today. So I'm going to stop here, that there is a T is a linear map. And we are going to begin the next class from this idea that we have to now discuss in the next class. What is a linear transformation? How does linear transformation matter? Okay, what are its effects immediately and things like that. Okay. Yes. And of course, we are going to, if you want, we can talk about the eigenvalues of this linear transformation and all that. We will definitely do that, right? Okay. The eigenvalues are complex. It's not a coincidence. Okay, we'll talk about that. Yeah, all right. There is. I mean, of course, I mean, I wanted to actually tell you today that the eigenvalues are nothing but, I mean, it's actually a scalar multiple, right, of a vector. I mean, and that scalar multiple has some significance. But I mean, basically what we are going to talk about in the next lecture are linear transformations and eigenvalues, and some of the results that we have seen, we have used in principal component analysis. We are going to, show those results. Okay, all right. I am uploading everything to Classroom, guys. I mean, I have already uploaded the videos to Classroom. Okay, there is a separate folder. You all have access to the folder. I'm also uploading this to a YouTube channel, and I have linked that YouTube channel to the Classroom folder as well. Okay. I'm not using Quanta. I have just uploaded the course information on Quanta. Okay. All right, guys. Thanks.